So let's do a little example with gravity here. Let's suppose, for example, that we have a hill, the cliff, and there's a rock sitting on top of the hill, and the rock has a mass m. Let's say that the height of the hill from the top to bottom is h, has a height h. And now let's further suppose that the rock rolls down the hill. Well, when the rock rolls down the hill, it can generate a lot of entropy. It can break things that are in the way. It could even break into pieces itself as it rolls down. It could do a lot of damage. There's a lot of energy in that rock, and so then that energy comes from the gravitational energy, from this gravitational potential. So you could say that, so here's one way to figure out how much energy this rock has to give up when it goes from the top to the bottom of the hill. It starts with an initial energy, and that is the mass times little g times the height. Down here it has what I call a final energy, so I'll call that U final. That U final is the mass times little g times the height at the end, but the height at the end is 0. Up here the height is h, and down here the height is 0. So U final must be equal to 0, because anything times 0 is 0. So then I could say that the change in gravitational energy is delta for change in gravitational energy will be just mgh minus 0, which equals mgh. Now let's do an example and put some numbers in here. Let's just suppose, for example, that my mass was 2 kilograms and that my height was 3 meters. What would the change in potential energy be then? Let's plug in those numbers. Delta UG would be m times g times h. M is 2 kilograms. Little g is 9.8 meters per second squared. And h is 3 meters. Multiply all these numbers together. 2 times 3 is 6. 6 times 9.8 would be about 60 minus 48.8. I think should be about 58.8. And what are my units? Kilograms, meters, meters. Meters times meters is the same thing as meters squared. So I can write kilograms, meters squared per second squared. Fortunately, this also is equal to a very convenient unit, which we've used before. It's the unit for energy, and that happens to be joules. So this is equal to 58.8 joules. So that means that the rock has 58.8 joules more at the top than it has at the bottom. What could have happened to that energy between rolling from the top to the bottom of the hill? So what happens to this energy, 58.8 joules more at the top than it has at the bottom for gravitational energy? Well, that gravitational energy must have gone somewhere, so we can draw an energy diagram to show what happens to that. So this will be the hill, and at the beginning energy is carried by this mass, it's m, and at the beginning the strength of the strength, which is Vg, is high. At the end, the Vg is low, gravitational potential is low, same mass at the end, but the gravitational potential is actually 0. You could also say it's low. Now, there's energy carried in here at the beginning and no energy carried back out here. So overall, you could say that there's an energy flow to the right, which is 58.8 joules, to be precise. That must be carried away by something else. And as I said before, the rock rolls down the hill. As it rolls down, it might break itself into parts, it might crumble apart other rocks, cause some erosion. It might heat itself up by just all these constant impacts. So all those things are different ways that entropy can be created. This is an irreversible process too. Remember, if a rock is sitting still, you don't ever see it spontaneously roll back up the hill. That's because entropy would have to be destroyed in order to do that. You only see the rock roll down the hill, so you know that it must be an irreversible process, and entropy must be created. So here's entropy, here's entropy created, and that created entropy must carry away the 58.8 joules. So now we can make a general statement about things which are under the influence of gravity, and that is that in general, nature tends to make things fall from high Vg to low, low Vg. Vg is the same thing as height, so we could also say that things tend to fall from high places to low places.